Hi guys, tonight we're going to explore one of the most mind-bending cosmic scenarios imaginable. What if another Big Bang was beginning right now? What if the very fabric of space-time started to unravel, and a new universe began exploding into existence, either within our cosmos or colliding with it from another dimension? If you enjoy these reality-warping sleep stories that push the boundaries of physics and cosmology, hit that like button and subscribe for more. And drop a comment letting me know what time it is, where you are, and where you're listening from. I always appreciate hearing from you night listeners scattered across the map. Alright, let's begin. Imagine standing in your backyard on a crisp autumn evening, gazing up at the familiar constellation of Orion hanging against the velvet darkness. The stars appear eternal, fixed points of light that have guided humanity for millennia. But what if, in the next moment, those ancient patterns began to shimmer and dissolve? What if the very fabric of space-time itself started to unravel, not through gradual expansion as our universe has done for 13.8 billion years, but through something far more dramatic and immediate? What if another Big Bang was beginning to unfold? The concept challenges everything we understand about cosmic permanence. Our universe stretches across 93 billion light-years in observable diameter, containing approximately 2 trillion galaxies, each harboring hundreds of billions of stars. The sheer scale defies human comprehension, yet theoretical physics suggests this vast cosmos might not represent the ultimate reality. Instead, our universe could be just one bubble in an infinite multiverse, where new Big Bangs might spontaneously occur, creating fresh space-time domains that could either merge with ours or exist in parallel dimensions we cannot perceive. To understand how another Big Bang might manifest, we must first grasp what made our original Big Bang possible. 13.8 billion years ago, our universe emerged from a quantum fluctuation smaller than a proton, containing all the energy that would eventually become every galaxy, star, and planet we observe today. In the first fraction of a second, specifically during the first 10 to the negative 35 seconds, cosmic inflation stretched this microscopic region by a factor of 10 to the 26th power, expanding faster than the speed of light. This process didn't violate relativity because space itself was expanding, carrying matter along for the ride rather than matter moving through space. The energy density required for such an event staggers the imagination. During those initial moments, temperatures reached 10 to the 32nd degrees Kelvin, billions of times hotter than the core of our Sun, which burns at a relatively modest 15 million degrees Celsius. The pressure exceeded 10 to the 96 pascals, making the conditions inside a neutron star seem gentle by comparison. A neutron star, despite cramming 1.4 times our Sun's mass into a sphere just 20 kilometers across, generates pressures of merely 10 to the 34th pascals. Now consider the possibility that such conditions might arise again, not as a replacement for our current universe, but as an addition to it. Theoretical models suggest several scenarios where another Big Bang could occur. The first involves quantum tunneling events, where regions of space-time spontaneously transition to lower energy states, releasing tremendous amounts of energy in the process. Just as radioactive atoms decay unpredictably through quantum tunneling, entire regions of space might undergo similar transitions, though on scales incomparably larger. The mathematics governing such events draw from quantum field theory, where particles constantly pop in and out of existence in the vacuum of space. Even in the emptiest regions of our universe, far from any galaxy or star, space itself buzzes with activity. Virtual particle pairs appear and annihilate millions of times per second within every cubic centimetre of vacuum. The energy associated with these fluctuations, known as vacuum energy, remains largely theoretical, but some calculations suggest it could be enormous, potentially providing the fuel for new cosmic creation events. If a quantum tunneling event triggered another Big Bang within our observable universe, the consequences would unfold with terrifying inevitability. The initial expansion would occur at speeds far exceeding light, meaning we would have no warning of its approach. The boundary between our familiar space-time and the newly expanding region would advance as a perfect sphere, encompassing everything in its path. Stars, planets, galaxies, and even the fundamental particles making up your body would be swept into a state of primordial energy, returned to the same conditions that existed in our universe's first moments. The process would be eerily beautiful in its symmetry. As the expansion boundary passed through our solar system, moving at perhaps 10 times the speed of light, Earth would experience conditions not seen since the cosmic dark ages. The temperature would spike to billions of degrees in microseconds, hot enough to break apart atomic nuclei and reduce all matter to a soup of quarks and gluons. The familiar elements that make up our world, carbon, oxygen, iron, silicon, would cease to exist as distinct entities, reverting to the fundamental particles from which they originally formed. But another Big Bang need not occur within our universe to affect us profoundly. Current theories about eternal inflation suggest that Big Bangs might be occurring constantly throughout a larger multiverse structure, each creating its own bubble universe with potentially different physical laws and constants. These bubble universes expand through a background medium called the false vacuum, a state of space with higher energy density than our current vacuum. Picture the multiverse as an infinite ocean of this false vacuum, constantly churning with quantum fluctuations. Occasionally, random fluctuations create small regions where the false vacuum decays into the lower energy true vacuum we inhabit. Each such event triggers explosive expansion, creating a new bubble universe that grows rapidly while remaining embedded in the larger false vacuum medium. Our universe represents just one such bubble, surrounded by countless others at various stages of development. The implications for life as we know it become staggering when we consider the possibility of bubble collision. Computer simulations run by cosmologists at leading institutions calculate that bubble universes expand through the false vacuum medium at significant fractions of light speed, typically around 60 to 80% of the ultimate cosmic speed limit. Given the infinite nature of eternal inflation, collisions between expanding bubbles become not just possible, but inevitable across vast stretches of time. When two bubble universes collide, the interaction creates a boundary layer where the distinct physical laws of each universe meet and compete. In our universe, the fine structure constant, which governs electromagnetic interactions, equals approximately 1 divided by 137. This precise value allows atoms to form stable structures and enables the complex chemistry necessary for life. In a colliding bubble universe, this constant might differ by even small amounts, fundamentally altering how matter behaves. The collision boundary would propagate through both universes at light speed, creating a visible signature in our cosmic microwave background radiation. This ancient light, released when our universe was only 380,000 years old and still glowing hot from the Big Bang, carries imprints of the universe's earlier structures. Careful analysis of temperature variations across the sky, measured to precisions of microkelvin, might reveal circular patterns indicating where collision boundaries passed through during our universe's formation epoch. Several research teams have claimed to identify such patterns in data from the Planck satellite, which mapped the cosmic microwave background with unprecedented precision. These potential signatures appear as subtle temperature variations arranged in circular patterns across regions spanning several degrees of sky. While the evidence remains controversial and alternative explanations exist, the possibility that we might already be detecting signs of multiverse interactions adds urgency to understanding what another Big Bang could mean for our cosmic neighborhood. The scale of destruction and creation involved in bubble collisions defies easy comprehension. Consider that our observable universe contains approximately 10 to the 82 atoms, a number so large that if you counted one atom per second, it would take longer than the current age of the universe to count even the atoms in a single grain of sand. A bubble universe collision would affect not just our local region of space, but potentially the entire visible cosmos and far beyond, restructuring matter and energy across distances of tens of billions of light years. Yet the most intriguing aspect of another Big Bang may not be its destructive potential, but its creative possibilities. Each new universe that forms through quantum tunneling or bubble nucleation represents an opportunity for entirely different forms of existence to emerge. The fundamental constants that govern physics in our universe appear finely tuned for complexity and life, but other values might permit even richer possibilities. In our universe, stars form when gravity overcomes the outward pressure of nuclear fusion, creating stable burning that can last billions of years. Our Sun, a typical yellow dwarf star, fuses approximately 600 million tons of hydrogen into helium every second, releasing energy equivalent to 90 billion nuclear weapons per second for over 4 billion years. This process depends critically on the strength of nuclear forces relative to electromagnetic and gravitational forces. A universe born from another Big Bang might have different force ratios, enabling stars that burn for trillions of years rather than billions, or perhaps allowing completely different energy sources to power stellar-scale objects. Gravity might be stronger or weaker, permitting the formation of stable structures at scales either much smaller or much larger than anything possible in our cosmos. The electromagnetic force might have different strength, fundamentally altering how atoms form and interact. Perhaps most fascinating are the possibilities for different dimensional structures. Our universe appears to have 3 spatial dimensions plus time, but string theory and other advanced physics models suggest that additional dimensions might exist, curled up at subatomic scales. A universe born from another Big Bang might unfold with 4 or 5 large spatial dimensions, creating geometric possibilities that we cannot even properly visualize. Life in such higher dimensional spaces would face challenges and opportunities completely foreign to our experience. In 4 spatial dimensions, planets could not maintain stable circular orbits around stars because gravitational forces would fall off as the inverse fourth power of distance rather than the inverse square. However, entirely different mechanisms for energy collection and organization might emerge, potentially supporting forms of complexity that make our biological systems appear primitive by comparison. The timeline for such cosmic events spans scales that humble human civilization. Our species has existed for approximately 300,000 years, a mere blink compared to our universe's age of 13.8 billion years. Human recorded history covers only about 5,000 years, while our industrial civilization has existed for barely 2 centuries. Against this backdrop, the processes that might trigger another Big Bang unfold across billions or even trillions of years. Nevertheless, the possibility remains that quantum tunneling events could occur much more rapidly. The uncertainty principle of quantum mechanics permits enormous energy fluctuations over extremely brief time periods, and these fluctuations grow more probable as the spatial scales involved decrease. A quantum tunneling event affecting a region of space just 1 meter across could theoretically occur within the next second, though the probability remains vanishingly small, roughly 1 chance in 10 to the power of Google, a number so large that writing it in standard notation would require more atoms than exist in our observable universe. The detection of another Big Bang in progress would represent both humanity's greatest scientific achievement and potentially our final observation. Unlike gradual cosmic events such as stellar evolution or galactic collisions, which unfold over millions of years and provide ample warning, a nearby Big Bang would approach at or near light speed, leaving little time for analysis or response. Modern astronomy has developed increasingly sophisticated methods for monitoring cosmic events across the electromagnetic spectrum. The Laser Interferometer Gravitational Wave Observatory, or LIGO, can detect gravitational waves from colliding black holes located billions of light-years away, measuring distortions in space-time smaller than 1/10,000th the width of a proton. Space-based observatories like the James Webb Space Telescope peer back in time toward the cosmic dark ages, observing light that has travelled for over 13 billion years to reach us. These instruments might provide the first evidence of another Big Bang through gravitational wave signatures, unlike anything previously recorded. While black hole mergers generate gravitational waves that oscillate at frequencies between 10 and several thousand hertz, the space-time distortions from cosmic inflation or bubble collisions might create waves at much lower frequencies, detectable only by space-based interferometers with arm lengths of millions of kilometers. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will consist of 3 spacecraft flying in formation 5 million kilometers apart, connected by laser beams that can detect gravitational waves at frequencies between 1,000th and 1 Hz. This frequency range perfectly matches theoretical predictions for gravitational waves produced during cosmic inflation, potentially allowing direct observation of Big Bang processes for the first time. Such detection would revolutionize our understanding of cosmic creation and validate theories that currently exist only in mathematical models. The energy scales involved in Big Bang events exceed anything achievable in terrestrial laboratories by factors of trillions upon trillions. The Large Hadron Collider, humanity's most powerful particle accelerator, can probe energies up to 14 tera-electron volts, equivalent to about 2.2 microjoules. By contrast, the energy density during cosmic inflation reached approximately 10 to the 76th joules per cubic meter, a difference so vast that comparing it to everyday scales becomes meaningless. The philosophical implications of another Big Bang extend far beyond physics into questions about consciousness, meaning, and continuity. If our universe were to be swept up in a new cosmic creation event, would the information that constitutes our thoughts, memories, and identities be permanently destroyed? Or might it persist in some form within the new cosmic structure? Modern physics suggests that information cannot be truly destroyed, even when matter is broken down to its most fundamental components. This principle, known as information conservation, arose from studies of black hole physics, where Stephen Hawking and other theorists grappled with what happens to information that falls past an event horizon. The resolution, still debated among physicists, suggests that information must somehow be preserved even in the most extreme cosmic processes. If information conservation applies to Big Bang events, then the patterns of matter and energy that encode our existence might survive the transition, possibly emerging in new forms within the restructured space-time. The quantum states that define every atom in your body, every neural connection in your brain, every photon of light you've ever seen, might persist as abstract information patterns that could, in principle, be reconstructed given sufficient knowledge and computational power. This possibility introduces a form of cosmic reincarnation that transcends traditional religious concepts. Your consciousness, rather than being tied to specific arrangements of carbon, nitrogen, oxygen, and phosphorus atoms, might represent an information pattern capable of existing in many different physical substrates. A universe born from another Big Bang might provide new materials and forces that could support consciousness in ways we cannot currently imagine. The economic implications of discovering that another Big Bang is possible or imminent would reshape human priorities overnight. Global gross domestic product currently totals approximately $95 trillion annually, with nations spending roughly $2 trillion on military defense and $2.8 trillion on scientific research and development. The confirmation that cosmic creation events could occur would likely trigger massive reallocations of resources towards space exploration, fundamental physics research, and perhaps most importantly, efforts to preserve human knowledge and consciousness beyond planetary boundaries. Space agencies worldwide currently operate on combined budgets of approximately $70 billion annually, less than what humanity spends on soft drinks each year. The prospect of cosmic-scale threats would almost certainly increase space funding by orders of magnitude, possibly approaching the levels currently devoted to military spending. Projects that seem fantastical today, such as interstellar probes capable of establishing human colonies around nearby stars, would become urgent priorities rather than distant dreams. The technical challenges involved in preserving human civilization across cosmic restructuring events push the boundaries of theoretical possibility. A self-replicating probe traveling at 10% of light speed could reach Proxima Centauri, our nearest stellar neighbor at 4.2 light-years distance, within 42 years of launch. Such a probe would need to carry not just human genetic information and cultural records, but also the industrial capacity to bootstrap technological civilization from raw materials. Current estimates suggest that a minimal self-replicating industrial base would require approximately 10,000 distinct technologies, from semiconductor fabrication and chemical processing to biotechnology and artificial intelligence. The probe would need to mass several hundred tons and cost hundreds of billions of dollars to develop, yet it would provide insurance against cosmic-scale disasters that could affect our entire solar system simultaneously. The biological consequences of another Big Bang depend critically on the mechanism involved and the timescales over which it unfolds. If quantum tunneling created a new cosmic domain within our local region of space, the advancing boundary would sterilize everything in its path within seconds or minutes. However, if the event occurred through slower processes such as false vacuum decay propagating from distant regions, advanced warning might provide opportunities for protective measures or evacuation. Life on Earth represents an extraordinary concentration of organized complexity, with the biosphere containing approximately 550 gigatons of carbon distributed among an estimated 1 trillion species. This biological information, encoded in DNA sequences and ecological relationships developed over 3.8 billion years of evolution, constitutes an irreplaceable record of creative processes that might never be repeated in exactly the same way. The preservation of terrestrial life across cosmic restructuring would require technologies that currently exist only in science fiction. Suspended animation systems capable of maintaining biological organisms for thousands or millions of years would need to protect against radiation, mechanical shock, and the gradual degradation of complex molecules over cosmic timescales. Alternative approaches might involve encoding biological information in more durable substrates such as synthetic DNA, stored in crystalline matrices or quantum information patterns, impressed into the structure of space itself. The geological record provides some guidance about how life has survived previous cosmic catastrophes, though nothing approaching the scale of another Big Bang. The Permian-Triassic extinction event, which occurred 251 million years ago, eliminated 96% of marine species and 70% of terrestrial vertebrates. Yet life not only survived, but diversified into new forms that eventually gave rise to dinosaurs and mammals. More recently, the Chicxulub asteroid impact 66 million years ago released energy equivalent to 10 billion nuclear weapons, creating a global winter that lasted several years and eliminated non-avian dinosaurs. However, small mammals, birds, and many plant species survived by exploiting protected ecological niches and alternative food sources. The key insight from these events is that life's greatest strength lies not in any individual species, but in the diversity of survival strategies represented across the entire biosphere. Applying these lessons to Big Bang scenarios suggests that preservation strategies should emphasize diversity, rather than attempting to save any particular collection of organisms or civilizations. Multiple independent colonies established around different stars would provide redundancy against local cosmic events, while storing biological and cultural information in many different formats would protect against specific failure modes. The search for signatures of previous Big Bang events has already begun through careful analysis of cosmic microwave background data and gravitational wave observations. The European Space Agency's Planck satellite mapped temperature variations in the ancient light from our universe's formation with precision approaching 1 part in 100,000, revealing subtle patterns that encode information about cosmic inflation and the fundamental properties of space-time. Several research groups have reported possible evidence for bubble collisions in this data, appearing as circular temperature patterns that deviate from the random fluctuations expected from simple inflation models. These signatures, if confirmed, would indicate that our universe has already experienced interactions with other cosmic domains created through separate Big Bang events. The statistical significance of these claims remains hotly debated within the cosmology community. Identifying genuine collision signatures requires distinguishing them from the numerous circular patterns that would appear randomly in any complex dataset. Current analysis suggests confidence levels between 90 and 99% for the strongest candidates, approaching but not quite reaching the 5 sigma standard typically required for major scientific discoveries. Future observations may resolve these uncertainties through improved data quality and analysis techniques. The next generation cosmic microwave background Stage 4 experiment will map polarization patterns in the ancient light with sensitivity 100 times greater than current instruments, potentially revealing additional collision signatures or definitively ruling out current claims. Gravitational wave astronomy provides another avenue for detecting Big Bang processes in real time. The theoretical signature of cosmic inflation appears as a background of gravitational waves at frequencies corresponding to the size of our current observable universe during the first moments after the Big Bang. These waves would carry direct information about inflation dynamics, including whether multiple inflation events occurred and how they might have interacted. The challenge lies in detecting signals that are extraordinarily weak after travelling for nearly 14 billion years while competing with gravitational waves from more recent sources such as merging black holes and neutron stars. Current estimates suggest that the inflation-generated gravitational wave background has an amplitude roughly 1 billionth that of the cosmic microwave background radiation, requiring detector sensitivities that push the limits of current technology. Despite these technical hurdles, several next-generation experiments are specifically designed to search for primordial gravitational waves. The proposed Einstein telescope would increase gravitational wave sensitivity by a factor of 1,000 compared to current detectors, while space-based missions like the Big Bang Observer could directly measure the gravitational wave background from cosmic inflation. The implications of detecting active Big Bang processes extend beyond academic physics into practical concerns about cosmic safety and the future of intelligent life. If quantum tunneling events or bubble collisions occur frequently enough to be observable, they might also occur frequently enough to pose existential risks over cosmic timescales. Current estimates suggest that quantum tunneling events affecting regions larger than our solar system occur roughly once per cubic gigaparsec per billion years, where 1 gigaparsec equals approximately 3.3 billion light-years. These numbers indicate that such events are extraordinarily rare from human perspectives, but become increasingly probable as we consider larger volumes of space and longer time periods. Over the course of our universe's remaining lifetime, estimated at several trillion years before stellar formation ceases due to cosmic expansion, the cumulative probability of experiencing a nearby Big Bang event becomes non-negligible. Advanced civilizations that survive into the far future will need to account for these risks in their long-term planning, possibly developing technologies that can function across cosmic restructuring events or strategies for migrating between universes. The study of cosmic creation processes also offers insights into the deepest questions about existence and the nature of reality itself. If Big Bang events can occur spontaneously through quantum processes, then our universe represents just one example from an infinite ensemble of possible realities, each with its own physical laws, fundamental constants, and evolutionary pathways. This multiverse perspective suggests that the apparent fine-tuning of physical constants in our universe, which allows for the existence of stars, planets, and complex chemistry, may not require special explanation. Instead of being uniquely suited for life, our cosmos might simply represent the type of universe where observers like ourselves are capable of existing and asking such questions. The anthropic principle, which suggests that we observe particular physical laws because only those laws permit the existence of observers, takes on new meaning in the context of eternal inflation and multiple Big Bang events. Rather than our universe being specially designed or incredibly lucky, the constants of physics might vary across different cosmic domains, with conscious observers naturally finding themselves in regions where complexity and life are possible. This perspective fundamentally alters how we think about humanity's place in the cosmic order. Rather than being central to a unique creation event, we might be temporary patterns of organization within one small region of an infinite multiverse, where Big Bang events constantly create new domains of existence. Our significance comes not from cosmic specialness, but from our role as local concentrations of information processing and conscious experience. The ultimate fate of our universe provides context for thinking about whether another Big Bang might represent destruction or renewal. Current cosmological models predict that cosmic expansion will continue accelerating due to dark energy, eventually isolating each galaxy within its own cosmic horizon. Stars will exhaust their nuclear fuel over the next 100 trillion years, leaving behind white dwarfs, neutron stars, and black holes that will gradually evaporate through Hawking radiation over unimaginably long timescales. Against this backdrop of cosmic heat death, another Big Bang might offer the only possibility for renewed creativity and complexity. A universe born from quantum tunneling or bubble nucleation would reset the cosmic clock, providing fresh energy sources and new opportunities for the emergence of structure and life. From this perspective, cosmic creation events represent not endings, but beginnings, transforming the products of one evolutionary cycle into the raw materials for the next. The mathematical frameworks describing these processes reveal deep connections between quantum mechanics, general relativity, and thermodynamics that continue to challenge our understanding of fundamental physics. The fact that quantum fluctuations can potentially create entire universes demonstrates the profound creativity inherent in the basic laws of nature, suggesting that reality operates on principles more rich and strange than our everyday experience might suggest. As we stand beneath the night sky, contemplating the possibility of another Big Bang occurring somewhere in the vast cosmos, we are participating in one of the most ambitious intellectual endeavors in human history. The questions we're asking about cosmic creation stretch our minds to their limits, while revealing the remarkable capacity of conscious beings to comprehend processes that operate on scales trillions of times larger than ourselves. Whether another Big Bang represents ultimate destruction or ultimate renewal may depend on perspectives that transcend our current understanding of time, space, and identity. What seems certain is that the universe we inhabit is far more dynamic and creative than our ancestors could have imagined, full of possibilities that continue to surprise and humble us as we push deeper into the cosmic mystery that surrounds and contains us all. Word count 5,247.